What if the oldest object ever measured passing through our solar system wasn't from our solar system at all? Right now, an object called 3I Atlas is heading back out into deep space. And according to new research using the James Webb Space Telescope, it may have formed somewhere between 10 and 12 billion years ago. That's nearly 3 times older than our entire solar system. That's old enough that the star system it originally came from may not even exist anymore. Let's start with the numbers, because they're what make this discovery genuinely remarkable without any exaggeration needed. 3I Atlas is only the 3rd interstellar object ever confirmed passing through our solar system, after Oumuamua in 2017 and 2I Borisov in 2019. Potentially places its formation during a period astronomers call cosmic noon, when star formation across the early universe was at its most intense, up to 12 billion years ago, putting it just under 2 billion years younger than the universe itself. Here's the part of this story that almost no coverage explains properly, and it's the part that matters most. This isn't just an old object drifting through space. Its chemistry is unlike anything scientists have ever measured in a comet before, containing an unusual mix that includes an isotopic fingerprint pointing to its ancient age, a strange abundance of heavy hydrogen, and a genuinely bizarre detection of nickel gas with essentially no iron alongside it. A combination that has never been recorded in any comet from our own solar system. That last finding specifically is what's fueled months of public speculation about whether this object might not be entirely natural. Today, we're going to walk through exactly what scientists have confirmed, what remains genuinely puzzling, and separate the real published science from the speculation that's been swirling around this object since the day it was discovered. The very first chemical red flag showed up months before the age estimate, or the nickel anomaly, ever made headlines. Back in August 2025, roughly 2 months after 3I Atlas was first spotted, follow-up observations, combining ground-based telescopes with James Webb data, revealed something scientists hadn't expected. The comet's coma showed a surprisingly high amount of carbon dioxide relative to water, vapor, an imbalance well outside the normal range measured in comets that formed within our own solar system. Most solar system comets release far more water than carbon dioxide as they're warmed by sunlight, since water ice tends to dominate their composition. 3I Atlas didn't follow that pattern at all, and researchers at the time submitted their findings as preprint papers to the Archive platform, flagging the CO2-rich composition as something that would need serious follow-up investigation. That early, unusual carbon dioxide signature turned out to be the first thread in what became a much larger pattern of anomalies, one that ultimately led researchers toward the isotopic analysis that produced the eye. Catching 10 to 12 billion year age estimate months later, I'm the host here at Today Latest Analysis, and every claim in this video comes from actual published research, including NASA's own official findings and peer-reviewed journal papers, not exaggerated headlines or unverified speculation. Subscribe now and turn on notifications, because this object is still being studied right now, and there's more coming. Let's start from the beginning. Because to understand why 3I Atlas matters this much, you need to understand what makes an interstellar object so rare in the first place. Every comet and asteroid we've studied throughout most of the history of astronomy formed somewhere inside our own solar system, orbiting our sun the same way Earth does. Interstellar objects are fundamentally different. They form around other stars entirely, sometimes get flung out of their home systems by gravitational interactions with planets over billions of years, and then drift silently through the emptiness between stars for unimaginable stretches of time before, by pure chance, one of them passes close enough to our sun for us to actually detect it. Oumuamua, discovered in 2017, was the first confirmed example, and its strange elongated shape and subtle unexplained acceleration sparked genuine scientific debate, along with a wave of public speculation about whether it might be artificial. 2I Borisov, discovered in 2019, behaved much more like a typical comet, reassuring most scientists these visitors, while incredibly rare, aren't inherently mysterious by nature. 3I Atlas is only the 3rd object of this kind ever confirmed, and it immediately became one of the most closely studied objects in the sky, with observatories around the world, including the Very Large Telescope in Chile and NASA's own James Webb Space Telescope, all turning their instruments toward it before it disappeared back into deep space for good. Here's how scientists actually determined its age, and the method itself is worth understanding, because it's genuinely clever detective work. As 3I Atlas began moving away from the sun in December 2025, having just made its closest pass and been freshly warmed by sunlight, its ancient ice converted into a bright, active coma of gas, exactly the conditions scientists need for detailed spectroscopic study. A research team used Webb's Near-Infrared Spectrograph, known as NIRSpec, led by scientist Martin Cordner at the Catholic University of America, working with NASA's Goddard Space Flight Center to map the comet's specific chemical makeup as that gas streamed off its surface. What they found immediately stood out. The ratios of water, carbon dioxide, and carbon monoxide detected in 3I Atlas's coma were unlike anything measured in any comet native to our own solar system. But the truly striking result came from something more subtle than just the presence of these chemicals. It came from their isotopic composition, meaning the specific atomic variants of those elements present in the gas. Different isotopes form under different conditions in the universe's history. And by carefully measuring the carbon isotope ratios present in 3I Atlas and comparing them against models of how chemical elements have evolved across the galaxy over billions of years, a process scientists call galactic chemical evolution, researchers were able to work backward and estimate when and under what conditions this specific material must have originally formed. The result, published in a peer-reviewed paper in the journal Nature on June 22, 2026, estimated that 3I Atlas accreted its material roughly 10 to 12 billion years ago, following an early period of intense star formation in the Milky Way's history. As one outside researcher, Romain Maggiolo of the Royal Belgian Institute for Space Astronomy, explained it, this isotopic composition shows 3I Atlas formed in a stellar environment fundamentally different from our own, not only somewhere else in space, but at a much earlier point in the galaxy's entire history. Now here's the second layer of this story, the part that adds an extra dimension to just how strange this object's chemistry actually is. Alongside the isotopic age evidence, researchers also detected an unusually high abundance of enriched deuterium, sometimes called heavy hydrogen, in the comet's gas. Deuterium is a naturally occurring isotope of hydrogen, and while it does appear on Earth, notably as fuel used in nuclear fusion research, its presence in unusually high concentrations within 3I Atlas reflects something about the extremely cold conditions the comet's material originally formed in, not anything related to artificial technology, despite that specific detail understandably catching people's attention online given its association with fusion fuel here on Earth. Then there's the finding that's generated the most public speculation by far. Earlier observations using the Very Large Telescope in Chile detected nickel gas coming off 3I Atlas, but with essentially no iron alongside it. That's a genuine puzzle, because in every comet ever studied within our own solar system, nickel and iron typically travel together, vaporizing off a comet's surface at broadly similar temperatures as it's warmed by the sun. Finding one without the other doesn't fit that established pattern. And it's exactly the kind of unresolved anomaly that tends to attract dramatic explanations. Harvard astrophysicist Avi Loeb, a well-known and frequently controversial voice in discussions about interstellar objects, pointed to this specific nickel without iron signature as evidence potentially suggesting an artificial origin. At one point, stating publicly that industrially produced nickel alloys are the only place this kind of signature has previously been documented, and separately citing a Webb-based mass estimate suggesting the object could weigh as much as 33 billion tons, and a figure he described as at least 1,000 times more massive than any other interstellar object observed to date. Here's the direct, evidence-based answer to that speculation. Follow-up research, specifically investigating the nickel anomaly, has proposed a natural chemical explanation that doesn't require anything artificial at all. Scientists studying the data suggest the nickel atoms may be bound within specific types of molecules, potentially including nickel attached to carbon monoxide or other organic compounds that break apart and release nickel gas at significantly lower temperatures than would be needed to vaporize metallic nickel directly. If that mechanism holds up under further study, it would explain the missing iron naturally, since iron wouldn't necessarily be released through that same low-temperature chemical pathway without requiring any exotic or artificial explanation whatsoever. NASA's own official position, reflected in their published Webb research and public science communications, remains that 3I Atlas is a natural interstellar comet, an extraordinary and scientifically valuable one, but a comet nonetheless, consistent with the broader body of evidence collected across multiple independent observatories. It's worth addressing the mass claim specifically, since it's one of the most widely repeated pieces of the speculation around this object. The 33 billion ton figure Loeb has cited publicly is not the mainstream mass estimate accepted by the broader research community studying 3I Atlas. Most estimates of the comet's nucleus, based on its measured brightness and standard assumptions about cometary reflectivity, put it at a scale broadly consistent with 2I, Borisov, and other known comets, not some dramatic outlier 1,000 times more massive than anything previously observed. Extraordinary mass estimates like lobes typically rely on specific assumptions about the object's density and behavior that most other researchers studying 3I Atlas do not consider well supported by the current data. This is a useful example of how the same raw observations can lead to wildly different conclusions depending on which underlying assumptions a particular researcher chooses to apply, which is exactly why peer review, multiple independent teams checking each other's work before conclusions get published in a journal like Nature, matters so much for a genuinely strange object like this one. That distinction matters because it separates genuine, still developing scientific uncertainty from outright speculation. It's true that the nickel without iron ratio remains a genuinely open question that researchers are actively working to fully explain. It's also true that isolated claims about artificial origin, mass estimates, or supposed engine signatures have not been supported by the peer-reviewed research published on this object, including the Nature paper establishing its ancient age. Good science is comfortable holding both of those facts at once, acknowledging a real, unresolved chemical puzzle, while not leaping to the most dramatic possible explanation before the evidence actually supports it. So here's what this discovery actually means once you separate the confirmed findings from the speculation. If 3I Atlas genuinely formed 10 to 12 billion years ago, it represents a physical sample of material from an era of the universe scientists have never had direct access to before. The early Milky Way, during a period of intense star formation long before our own sun, our solar system or Earth existed in any form. Every previous comet ever studied up close formed within our own solar system's roughly 4.6 billion year history. 3I Atlas potentially offers scientists their first ever direct chemical sample from a completely different, much older stellar environment, effectively a frozen time capsule that's been drifting through interstellar space for billions of years before happening to pass close enough to our sun for us to study it at all. It's worth taking a moment to explain what astronomers actually mean by cosmic noon, since it's easy to gloss over that phrase without understanding why it matters. Cosmic noon refers to a specific era in the universe's history, roughly 10 to 12 billion years ago, when galaxies across the cosmos were forming new stars at a far higher rate than they do today. Our own Milky Way was still actively assembling itself during that period, and heavy elements like carbon, nickel, and iron were being forged and scattered through space by generation after generation of massive stars living fast and dying young. If 3I Atlas truly formed during that window, its raw material was gathered from a version of the galaxy that looked nothing like the calmer, more settled Milky Way we live in today, one still churning with far more star formation, far more supernova explosions, and a fundamentally different mix of raw chemical ingredients than existed by the time our own sun and solar system formed billions of years later. This has real implications for how astronomers understand planet formation more broadly. If comets forming in very different, much older parts of the galaxy carry distinctly different chemical signatures than the comets that formed in our own solar system, it suggests the raw ingredients available for building planets and comets weren't uniform throughout the galaxy's history. They varied significantly depending on when and where a given star system happened to form. That's a genuinely important data point for scientists trying to understand how common, or how different, planetary systems across the Milky Way actually are compared to our own. There's no evidence 3I and Atlas poses any threat to Earth whatsoever. Its trajectory has been tracked closely by multiple independent observatories, and it is already moving back out of our solar system on a path that will carry it into interstellar space for good, never to return. What makes it genuinely remarkable isn't danger, it's rarity in age. Scientists get an opportunity to study material this old, from an environment this different from our own solar system, extraordinarily rarely, and 3I Atlas is only the third such opportunity in recorded astronomical history. I'll bring you the next update the moment any new peer-reviewed research resolves the nickel without iron puzzle, or if any additional observatories add new data before 3I Atlas moves permanently out of range. If you want deep space mysteries and James Webb discoveries explained accurately, separating what's actually confirmed from what's still speculation. That's exactly what we do here every single time. Drop a comment and let me know what part of this surprised you most: the extreme age, the missing iron alongside the nickel, or the unusually high deuterium signature. Like, subscribe, and turn on notifications so you don't miss the next update on this object, and I'll see you in the next one.